Hello students. In the previous videos, we discussed about crystalline solids which has completely ordered, or we can say a perfect arrangement of particles, in which we have discussed one dimension of arrangement, two dimension of arrangement, three dimension of arrangement. So what we have seen that in crystalline solid there is a perfect arrangement of particles. But you know that no one is called as perfect. There will be some defects in that. So, in crystalline solids also have certain defects. So, let us discuss imperfection in solids, or we can say defects in solids. As we have learned that there are two types of solid, that is crystalline solids and amorphous solids. In the crystalline solid, we have learned that there is a perfect, or we can say definite arrangement of particles. As shown in the figure, you can see all the particles are in a regular fashion or regular manner. But in amorphous solid, it is in a random arrangement. So, if we consider an ideal crystal, ideal means perfect in all the way. Let us take a crystal system which is taken as ideal. In this structure you can find that there is alternate cations and anion. A positive is the cation, B negative is the anion, then cation, anion. That means you can see all cations and anions are arranged alternately to each other. That means throughout the crystal the arrangement of cation and anion are in this way. That means they are alternate to each other. And you can see the position of cations and anions are in ordered manner. That means the particle is completely ordered, or we can say arranged in a particular manner. Such type of crystal is called as ideal crystal. That means ideal crystal means which have completely ordered arrangement of particles. And even there is a throughout the crystal there will be a same pattern of unit cell also. Such type of crystal is called as ideal crystal. Let us define what is ideal crystal and what is defect. When it is called as a defect, let if one of the particle is missing from here, let I am marking this one. If any one of the particle is missing, then it is not called as ideal. Why? Because now when you look at the pattern, it is not in a regular manner, because after B negative there is A positive and after that again A positive. So that means a missing of a single particle from a crystal make a crystal imperfect, or we can say it have defect. So that is about the imperfection in solids, or we can say defect in solids. Let us define ideal crystal and defects in solid. Definition of ideal crystal. An ionic crystal which has the same unit cell containing the same lattice points throughout the whole of crystal is known as ideal crystal. It means if we consider a crystal to be ideal, in that throughout the crystal there will be same unit cell. Same unit cell means if it is cubic, throughout the crystal it will be cubic only. And it have same lattice point. Lattice point means the particles which we are there at in the crystal, and that arrangement will be also throughout the crystal will be same. That type of a crystal is called as ideal crystal. And if any deviation from the completely ordered arrangement in a crystal constitute particle is called as defects in solid, or we can say imperfections in solid. Let us discuss more about defects in solids. Defects are broadly classified into two categories, that is point defect and line defect. What is a point defect? Point defects are the irregularities, or we can say deviation from ideal arrangement around a point or an atom in a crystalline substance. That means, as we have discussed, in a crystal lattice, point means the particles which are found at the lattice point is called as points. So if there is any irregularity in the arrangement of the points means the particles which is at the lattice point. If such arrangement are irregular, then it is called as point defect. And line defects are the irregularities or deviation from the ideal arrangement in the entire row of lattice point. That means if any irregularity throughout in the entire row of lattice point, in point defect only there is irregularity at a particular point. That means the point means the particle on which a particular lattice site. But in the line defect, the entire row, that means we can say a line of particles are irregularly arranged. Then it is called as line defect. But in our syllabus, we need to discuss only point defects. So let us discuss point defects in detail. Point defects can be classified into three types. That is stoichiometric defect, non-stoichiometric defect and impurity defect. As shown in the figure, some particles are missing from the crystal lattice. You can see here one particle is missing. Which particle it should be here? It should be B negative. B negative is missing from here. It is not there in the system, in the crystal lattice, and here one A plus is missing. That means now this particle is not perfectly ordered, or we can say there is no perfect arrangement of points. So such defect is called as point defect. Let us discuss the three categories of point defect one by one. First, let us discuss stoichiometric defect, and let us find what is the difference between stoichiometric defect and non-stoichiometric defect. As shown in the first case, when you look at the two structure, in this structure you can find two particles are missing. This is a sodium chloride crystal lattice is shown, in which there is an alternate Na positive Cl minus, Na positive Cl minus. This is the ideal case. We can say it is an ideal crystal. Look at the second picture. In this picture you can find two particles are missing. But still the ratio is 1:1. As here the ratio between Na plus and Cl minus is 1:1. Because how many numbers of positive ions are there? That much number of negative ions are there. So we can say the ratio between the Na plus and Cl minus is 1:1. But in this defect, you can find two particles are missing. That is, one Na plus is missing from here, one Cl minus is missing from here. But still the ratio between these, because equal number of positive and negative ions are missing. So we can say that the ratio is again 1:1 ratio. So such type of defect which does not disturb the stoichiometry of the compound is called as stoichiometric defect. That means stoichiometric defects, these are the point defect that do not disturb the stoichiometry of the solid. We can say it does not disturb the formula of the solid, because here also the formula of sodium chloride is NaCl. Here also the formula is NaCl. That means its stoichiometry, there is no change in the stoichiometry of the substance. Such type of defects is also called as intrinsic or thermodynamic defects. Let us go through the non-stoichiometric defect. Why it is called as non-stoichiometric defect? Because in this case, the ratio what we have here, cation is to anion ratio, is not equal to the cation anion ratio in the defect. If this is an ideal, and in the defected one you can see, now the ratio here is the ratio is 1:1 ratio, but here the ratio is not 1:1. It is 0.95:1 ratio. That means the ratio between the two is not same. So that means this type of defect disturb the stoichiometry of the solid. Therefore, such type of defect is called as non-stoichiometric defect. So let us discuss stoichiometric defect in detail. Let us look at the structure. In the first structure, you can find some particles are missing. Let us check out which particles are missing. One particle is missing from here, one particle is missing from here. Because when the particle is get removed from the lattice, it develops a hole. You can see the two particles, that is A positive and B negative. It is now get removed from the crystal lattice. So what it develops? It develops a hole there, that is marked as dark black. So it develops a holes, or we can say it develops a vacancy in the crystal lattice point. Therefore it is called as vacancy defect. Vacancy means a empty space. So here, due to the removal of points from a lattice point, it leaves a hole, or we can say it leaves a vacancy at that site. Such defect is called as vacancy defect. For example, if any one of the student is not present in the class, so the place of that student will be vacant. So what we can find, there will be a vacancy at that place. Similarly, in a crystal lattice, the particles are arranged properly, and if any one or two particle, if it is not there in the system, in the crystal system, it remains there a vacancy, which is called as vacancy defect. But look at the second one. In the second structure, that is the second structure, in this you can find that all the particles are there at the lattice point. These all are the lattice points. All particles are at their lattice point. But here one more particle is get entered into the crystal system. And since there is no place for that particle at the lattice point, so it occupy a space which is called as a void, or we can say a interstitial site. This is called as interstitial site. That means a vacant space between the particles are called as interstitial site. So the particles which is coming, it is occupying the space in the lattice sites, or we can say the vacant space between the particles. That defect is called as interstitial defect. Interstitial defect means when the particles are occupying the interstitial sites Such type of defect is called as interstitial defect. Let us take one example. If all students are present and their places are occupied, all the students have occupied their own places. But if new admission come, then the new student have no place for sitting. So that means in that case it will be sit somewhere other than the bench. So we can say that is a interstitial defect. This type of defect, that is stoichiometric defect, is classified in the ionic crystal as Schottky defect and Frankel defect. So these defects are quite important defect which is usually asked in exam. So let us discuss Schottky defect and Frankel defect in detail. Let us discuss Schottky defect. Look at an ideal structure which is given here. In this, there is perfect arrangement of the particles, that is alternate A positive and B negative arrangements are there. Now if two particles are missing from the lattice, you can find which one is missing. When you compare the two structure, this part is missing, which I will highlight here. This part is missing and here this part is missing. That means 1A plus and 1B minus is missing. So what it develops a vacancy, or we can say it develops a hole. You can see there is hole, or we can say a vacancy is there. Vacancy is there or hole is there. Because it develops a vacancy or hole, therefore this is also a vacancy defect. Since here equal number of cation and anions are missing, we can say the cation missing is equal to anion missing. Therefore, this type of defect is called as stoichiometric defect. Because since the particles which is cation and anions are missing, these are in equal number, so it does not affect the stoichiometry of the compound. That means if it is an NaCl, it is still NaCl, because the number of cations and anions are still they are in equal numbers. So such type of defect is called as Schottky defect. And this type of defect is a vacancy defect in the ionic solid, and in order to maintain the electrical neutrality, the number of missing cations and anions are equal. That means now after the defect, after the missing of particle, still this defect is called as electrically neutral. When you check the number of cations and anions, these are equal. So we can say it is electrically neutral. What happens if only the one cation or one anion is missing? So if only one cation anions are missing in the lattice, we can find that either the cation will be greater than the anion. So we can say that the crystal develops a positive charge. If B negative, that is anion, is greater than positive, then we can say that it will not be a neutral crystal, it will be a negatively charged crystal. But in the case of Schottky defect, equal numbers of cations and anions are missing. Therefore, we can say that this is electrically neutral. Is electrically neutral. That means the crystal is not neither positive nor negative. The crystal is electrically neutral crystal. So such type of defect is called as Schottky defect. Let us discuss Frankel defect. In Frankel defect, when you find it out and compare it with an ideal crystal, this is an ideal crystal which is shown here. When you compare this defect with an ideal crystal, what you can find that one of the particle is missing. Which particle is missing? Look at the two structure. Which particle? This particle is missing. That means A positive is missing from its own side, but it occupies the interstitial site. That means this cation is actually not get removed from the crystal system. It is still there in the crystal system, but actually it changed its position. That means it changed its position from the lattice point to the interstitial site. So you can find that here the A positive is actually occupying the interstitial site. That means the vacant space. It is occupying the vacant space between the particles. So such type of defect is called as a interstitial defect. Interstitial defect means the defect in which the particles are occupying the interstitial sites. So here also there is no difference in the formula. Why? Because the particles are still, it is still there in the system, and here also the number of cation and anion is equal. So we can say that it does not disturb the stoichiometry of the compound. So such defect is called as Frankel defect. Usually the smaller ion, that is cation, is actually delocalized from its normal site to an interstitial site. It creates a vacancy defect at its original site, that is the site. It causes a vacancy defect at its original site and an interstitial defect. That means it is vacant from its original site, but it occupies the interstitial site. Therefore, there is a vacancy defect also, interstitial defect also present in the crystal lattice. Such defect is called as Frankel defect. Let us discuss how this defect will affect the density. So in this case, when you look at the Schottky defect, here the particles are entirely, these two particles are entirely out of the crystal system. That means these particles are not present in the crystal lattice. Therefore, what we can say that the mass of the mass get reduced. So we can say that density also get reduced. Why? What is the relation between density and the mass? Density is equal to mass by volume. Because here particles are removed, it is not there in the system. You can find there is no, these two particles are not there in the system. So we can say that the mass of the mass get reduced. Therefore, automatically density also get lowered. So from this what we can conclude that due to Schottky defect, density decreases. But what about the Frankel defect? In the Frankel defect, as because the particle is missing from its own site, it occupies the interstitial site. We can say that the particle is still there in the crystal. It is not get removed from the crystal. It is still there in the crystal. So therefore, we can say that the mass will not get changed. Therefore, the density will not get changed. So the Frankel defect has no impact on density. That means due to this defect, the density will not get changed. So we have compared the density in Schottky defect and Frankel defect. So the density get lowered in Schottky defect, but the density will not get affected in Frankel defect. So let us do a comparative study between ideal crystal, Schottky defect and Frankel defect. So when you look at the structure, just recall the points whatever we have discussed. In the ideal crystal, there is perfect arrangement of particle, that is called as ideal. But in Schottky defect, particles are missing from its own site. Because of this, the density of the particle get lowered, and it usually found in the ionic crystals in which there is a small difference in the size of cation and anion. So this type of defect is usually found in the ionic solid in which the size between the cation and anion is very small differences there. So examples are NaCl, KCl, CaCl, and it usually found in the solid in which there is high coordination number. But in the Frankel defect, the particles are missing from its own site, but it is occupy the interstitial site. It is found in the ionic solids where it have low coordination number, and it found in the solid in which there is a large difference in the size of cation to the anion. So that means when there is a great variation in the size of cation and anion, in such case Frankel defect is found, because here the particle is occupying the interstitial site. So usually the smaller particle, that is a cation, is occupying the interstitial site, because the vacant space, the interstitial site is actually a very small size is there. So only the small size particle can occupy that place. So we can say that there should be a large difference between the cation and anion so that the Frankel defect takes place. The example of Frankel defect are ZnS, AgCl, AgBr. The further examples you can find it out from the text and add in this section. Impurity defect. If molten NaCl containing a little amount of strontium chloride, that is SrCl2, is crystallized, at the time it is observed that some of the Na plus ions are occupied by the strontium ion. When you look at the ideal system in this, here this point there should be Na plus, but Na plus is missing. But in the place of Na plus, there is a strontium ion. Here you can find a space, a hole in which there is no particle. Actually, there is a Na plus there which has left out. In this case, 2 Na plus ion is creating holes, and one of the hole is occupied by one strontium ion. So why it happens? 2 particles get removed, that is 2 Na plus get removed, and only one strontium ion is entered. That means in order to make the crystal as neutral. Therefore, we can say some of the Na plus sites are occupied by strontium ion, and in order to make electrical neutrality, we can say that one strontium ion get entered and 2 Na plus ion leave the crystal. Then only it will become electrically neutral. When you count the number of positive and negative ion, you will be getting equal number. That means this crystal is perfectly neutral. Some other examples of this type of impurity defect are, that is CdCl2, cadmium chloride, and AgC. Since why it is called as impurity defect? Because other than the own points, some other particles are entered into the system. So therefore we can say it is an impurity defect. Before getting into the non-stoichiometric defect, let us summarize the points which we have learned in this video. We'll be discussing non-stoichiometric defect in the next video. So let us summarize the points which we have discussed here. That is defects in the solid, which are of two types. That is point defect, line defect. Point defect, that means a defect arises due to the irregularity in the arrangement of particles or the points. These are of three types: stoichiometric defect, non-stoichiometric defect, impurity defect. As stoichiometric defect, we have discussed this type of defect will not disturb the stoichiometry. Therefore, it is called as stoichiometric defect. Impurity defect, in which we have taken the example of NaCl with strontium chloride, we can find out the particle other than the own particles get entered into the system. That's why we called it as impurity defect. Non-stoichiometric defect, in which it disturbs the stoichiometry of the compound, therefore it is called as non-stoichiometric defect. Stoichiometric defect is of two types, that is Schottky and defect, which we have discussed. So this is all we have discussed in this video. Now the details of a non-stoichiometric defect will be discussed in the next video. So all of you go through these defects in order and learn the examples of each type of defect. Non-stoichiometric defect will be discussed in the next video. Thank you everyone.